Hi, I'm Arushi. I'm a software engineer at Meta, and in my 5 years here, I worked on a few different teams: Zookeeper, Service Discovery, and lately Owl. Owl is our attempt at solving the data distribution challenge, and Jason and I are here to tell you how we achieve this at Meta. Data distribution is a pretty common problem. I'm sure all of you see this in your companies with binary distribution, container distribution, lately AI models, and also search indexes. The scope of this problem is quite vast. This data might be read by a few different machines, or thousands or millions of machines, even. The size of the object obviously varies widely and keeps growing as more data is being used by all of our systems. Additionally, the temporal locality of this data can have a wide impact on what solutions we pick for it. Is the data read almost immediately by these hosts, or is it read over a large period of time? In addition, the requirements of distribution are pretty exacting. The data should be delivered as fast as possible while using as few extra resources as possible. This means we must be fast and efficient, but that does not mean that we can make trade off on reliability. The system needs to be highly available, and operators must be able to react whenever the workload changes. At Facebook, we've had a few different solutions over time for tackling the data distribution problem. Our first attempt was pretty simple, which is to add hierarchical caches in front of our distributed data stores. This is a pretty standard solution where requests get routed to a caching machine, and on failure, requests are made to the backing store. This is pretty easy to operate and simple to understand. However, this means that we needed a dedicated pool of machines to act as a cache, and sometimes, when there were load spikes for a particular piece of content, certain machines could get overloaded and throttle the request from the client. This meant we were always struggling to provision appropriately, either trying to provision for the steady state or trying to provision for the spikes and wasting capacity. Our second solution that we had built was based on BitTorrent. BitTorrent is a well known protocol where there is a central set of trackers that keep a list of all peers that are caching chunks. A new peer wanting to fetch data can talk to the trackers, get a list of the peers that might have the data, and then fetch data directly from these peers. This scales really well for the data fetching part because it is peer-to-peer communication and is not bottlenecked on the trackers at all. However, since each peer is making its own individual decision, its state could be stale and it could be making suboptimal decisions for where to fetch data. The system is also hard to operate and debug because all of these decisions are being made independently on thousands of machines. Another system that we built at Facebook for doing data distribution was called Rex. It's similar to BitTorrent in the idea that the data distribution itself is distributed. However, the peer membership, instead of being kept in a set of trackers, is now kept in a Zookeeper instance. Each client then keeps a copy of this membership list such that it can make decisions using consistent hashing of where a particular piece of content should be fetched. This scales poorly on the control plane because the membership itself now needs to be known by every single host. And just like torrent, it has the problem of being hard to debug and operate because the decisions are all made independently by these peers. Over time, these systems started hitting scaling limits as we continued to use them for larger and larger amounts of data. In the hierarchical caching state, it was the data plane that started hitting the limits with and requiring more and more machines to be able to serve at the rate that we needed the data to be fetched. In the case of Rex and Torrent, what we found was that the operational overhead when things went wrong was much higher, and it made the overhead of operating these systems pretty high. With this, we decided to pause and reevaluate these options and see if there was something better that we could come up with that would allow us to work around these downsides of the existing systems and provide something better. Jason's now here to talk through what we learned from these existing systems and where we went from here.
Thanks, Arushi. I'm going to pause and introduce myself. I'm Jason Flinn. As you can tell from the Fenway picture, I grew up in Boston, but I came to Meta about 3 years ago to work on interesting distributed systems and that were really cutting edge and talk about them with my colleague, which is why I'm really excited to give this talk today. Now, getting back to OWL. Arushi talked about the prior systems we had at Meta and the challenges they faced. So the first thing we did was look at these prior systems and figure out what lessons we could take away from them. From Rex and BitTorrent, we learned it was really important to decentralize the data plane, which means use peer-to-peer distribution, because that's necessary to scale to meta size. From centralized hierarchical caching, we learned we needed to centralize the control plane in order to make the system easy to operate and manage. Now, BitTorrent had millions of client processes, and it was a real pain to manage those and distribute them and deploy them. And so we learned to keep them as simple as possible to minimize the need for that by a mechanism policy split. They just do really simple actions, and we want the control plane to stitch together those actions into complex policies. And the other lesson we took away is this can have an additional benefit. BitTorrent often made bad decisions because each decision was made on a peer with only local state. In contrast, hierarchical caching made much better decisions because it looked at the entire global state of the system when making those decisions. So we want to centralize the decisions for that reason. So now let's dive into the design of OWL that's motivated by these lessons. OWL has three components: peers, superpeers, and trackers. Now, a peer is just a library that's linked with a client that wants to download data. It has simple actions that include the ability to go and get data from an external data source or from another peer, and it can cache data on memory or on disk. A superpeer is a peer that isn't linked with the client process. Instead, it's on a machine that we manage and it has all the resources of that machine. So caches are long-lived, the caches are larger, and importantly, we can put functionality that isn't available on every host in the fleet on a superpeer, like the ability to read from a specialized data source. And the tracker is the key here. It's the brain of the system. So a tracker tells the peers and superpeers what to do and implements these policies for fetching and caching data. Let's see how this all works. First, a peer on the right wants to fetch data from an external data source. It doesn't know how to do this on its own. It asks its tracker. The tracker says, well, I can look at my global state. No peer has this data. We need to get it from an external data source. But don't get it directly. We're going to have a superpeer fetch it, and you should fetch it from the superpeer. And so this makes the data available for other peers in this long-lived cache. Now, this forms what we call an ephemeral distribution tree, where the data flows through the superpeer to the peer, and then as other peers ask for the data, the tracker will continue to build out this distribution tree. The key here is that each node in the tree sends out data as soon as it arrives, rather than waiting for an entire chunk of data to arrive. So this means that we only pay the first byte latency cost for indirection, not the store and forward cost of the entire chunk. Now you might look at this and say, well, clearly, Jason, this is not going to scale. You can't run the entire distribution load of Meta on one single machine. And of course it doesn't. We have to do something here. What we do is we shard this global state across a set of equally responsible trackers. Each tracker is responsible for managing a portion of the peers of the system, and the peers are randomly distributed among those trackers. What makes this work is that each tracker maintains the global state at two levels of resolution. For peers that the tracker manages locally, it maintains very fine-grained information. It knows what chunks each peer has cached, what chunks each peer is downloading, and where each of those peers is getting the chunks from. But for peers that it doesn't manage, it maintains the global state at a really coarse grain of information. It just maps peers to trackers that are responsible for them, and chunks to the trackers that are responsible for those peers. And this allows a peer that doesn't have a chunk locally to delegate the decision about where to fetch data to a tracker that does have that chunk available. A lot of words. Let's see how that works. So now we have two trackers. Our peers are sharded among them. The ones on the right are managed by tracker A. The others are managed by tracker B. So same as before, when a peer wants a chunk, it asks its tracker. And the tracker in this case will say, well, nobody has it. Let's get it from an external data source. But now this tracker advertises the fact that it has at least one peer that's downloading or caching that chunk. And other trackers can learn this. Now, if other requests come in for tracker A, it just builds out its ephemeral distribution tree. But when a peer that belongs to tracker B requests the chunk, we see something a little bit different. That tracker delegates the decision about where to fetch the data to tracker A. And tracker A selects one of its peers, and our ephemeral distribution tree now spans our shards. And each of these trackers can continue to build it out based upon their local state. So the key here is that even though we sharded state across multiple trackers, we still maintain the cache hit rate as if we had a single tracker. We only go to the external data source once. Now, I've given you a picture of the overview of the design of OWL. I'm going to throw it back to Arushi, who's going to talk about our flexible policy interface.
Thank you, Jason. Now that we've learned about the architecture of OWL, the next question is, how did we go about onboarding people onto this infrastructure? As we talked about in the introduction, there were 3 existing solutions already at Meta that were being used. Each of them had been specialized for the customers that it served, and everyone had slightly different key metrics that we cared about. So, how do we get them on one system without any regressions? The solution we came up with was to have a pluggable policy module in the tracker for each use case that could be used to decide what to cache, when to fetch, how to fetch. At the point of filming this, we have about 100 clients with 55 unique policies. The first type of policy that we added to our tracker was a selection policy. This decides where a given chunk should be fetched when a peer is requesting it. Additionally, this can be used to decide should we retry, when we should retry, which peer we should retry at, and so on and so forth. The thing this allows us to do is to set policy parameters like max outflows and bandwidth constraints that can be used to limit how much resources of a given peer we are using when fetching content from it. This means that we do not overwhelm the host by doing peer-to-peer fetches from it and allow it to do the operations that it needs to do for its business logic. Some examples of policies we have our location-aware policy, which tries to choose the nearest machine, peer or super peer, to fetch any piece of content. The second one that we added was a hot and cold policy that allowed us to leverage super peers just for the hot data when we expected a lot of peers to have to fetch it, and bypass it for cold data, thus preserving the cache space for the hotter content. The second type of policy we added was a caching policy. This determined that when a peer was fetching content, whether it should cache it, and if so, how it should cache it. Additionally, if a new chunk was fetched and needed to be cached, what we should evict from the cache. This meant that we were always in control of what was in a peer's cache and could keep a very up-to-date state of this in the tracker. One thing that it allowed us to do that we hadn't anticipated when we started was that we had some customers that were highly constrained on memory and could not provide additional resources for caching. However, they did keep the data that they read around to do processing on it. This meant that they had this data available in a read-only format that we could also use as a cache. Having a flexible component that allowed us to tack on caching policies that could reuse this data buffer meant that we could easily onboard this customer. Such types of customers actually manage their own cache replacement. However, the system is flexible enough to adopt this. Other replacement policies that we have are least recently used, least rare, TTL, and random. The hard part with having this pluggable model is actually how do you find the best policy? The idea that we came up with and implemented as part of an intern project was to actually capture traces of production runs of users' traffic, run actual trackers and emulated peers that would replay this traffic, and try and use different policy combinations to come up with the best results. We do this when we onboard new customers as well as on a regular basis. As we've added new policies and improved our system, we've found previous use cases that we can actually improve the metrics for due to this continuous search and emulation that we do. We've improved hit rate for a lot of customers by doing this offline analysis on a regular basis. With that, I'll hand off to Jason to talk about what the evolution of OWL at Facebook has looked like.
Thanks, Arushi. So we've talked about the challenges that prior systems had in distributing data at Meta, and we've talked about how the design of OWL addresses those challenges. Now you're probably curious to see how it works in practice, and so I'm going to show you some data. First, on this slide, we're showing you how the workload for OWL has increased over time. We started the project about 2 years ago, and since then we've had tremendous growth. This growth is both due to organic increase in downloads in Meta, but more importantly, we're replacing a lot of prior systems, and we're taking on their load. So this chart shows you in 2021 how OWL's load increased. The blue line is the amount of data being requested by clients, and you can see that increased by a factor of 200 during the calendar year. At the same time, the amount of resources we needed, machines for the control plane of OWL, increased only by a factor of 4. And the reason for this disparity is because we are using peer-to-peer distribution. This is a big win. Now, at the end of the year, we're handling a lot of data, over 700 petabytes of data every day, and over 10 million client processes every day. So what does a typical day look like then at the end of the year? Well, the blue line shows you the instantaneous data that's being requested by each of our client processes. The red line shows you the amount of data that we're fetching from external data sources. So the first thing you notice is, wow, there's a lot of peaks and valleys here, and the workload doesn't look very regular. You'd be right. It's very hard to predict this. There's no external diurnal cycle or anything that we can detect here. So we're getting really good scale out thanks to our peer-to-peer design here, and we're masking that. If you see that red line, it barely budges during the course of a day. There are no peaks and valleys. And in fact, we're getting a 95% cache hit rate, which is taking load off of our external storage. Finally, if you look at how we compare to other systems, we do really well. One of the fun things about rolling out is you can pause the rollout in the middle. So we were replacing BitTorrent in a region, which is a group of geographically located data centers. And we stopped at the point where half the machines were running OWL and half the machines were running BitTorrent. And we just measured things for a day. We ran a scientific experiment. And we found that the cache hit rate, a key metric used by OWL, was more than twice as good. The throughput at the median was twice as good, and OWL improved the tail throughput, the 95% throughput, by a factor of 5. Why is it doing so well here? When we analyzed it, we found that really the key was making centralized decisions based upon global state and OWL. BitTorrent made all of its decisions in peers, and that was based upon only local state visible to each peer, and so often it made poor choices, where OWL just simply made better decisions. Those added up over time. So, here are the main lessons that we learned from designing and building OWL. First, we learned that it's important to centralize the control plane for operability, but decentralize the data plane for scale. A mechanism policy split allowed us to have very simple, easy to operate peers while still maintaining tremendous flexibility in supporting different types of customers. Finally, we learned that emulation was really powerful for tuning our behavior for each individual customer and also adjusting for their workload changes over time. In the future, we have a lot of exciting directions. We're moving from pulling data to peers to pushing data to peers via streaming notifications. And we're also looking at adding incremental update capabilities for really large, rapidly changing objects like AI models. So I look forward to the future, and I really enjoyed giving this talk to you. Hopefully I'll be able to talk about these new innovations next time.